Hello, everybody. Hey, we are coming to you second period on Thursday, and we have another lecture, and this lecture is going to be on acceleration. So I'm about to ignore you guys on the video and talk to the people that are in second period. So anyways, what we've talked about before was velocity and graphs of position versus time, distance versus time, and then a little bit on speed and velocity versus time. And we will review that as we go through this lecture. All right, so you guys, the equation that I gave the other day, okay, was on average velocity. And if you guys did not catch this in the other video, with that bar over that means average, okay? And there's going to be a quiz probably Monday, and it should be an easy quiz, but I'm going to ask you a bunch of things about terminology, symbols, maybe a couple simple problems, okay? But that's one of them. That bar over the B, that's going to mean average, okay? And that was, okay, the change in position, okay? Now, I think in the lecture that I did before, I called that D or delta D, okay? And it could be in the X direction, it could be in the Y direction, it could be in the R, it could be any direction we want. But just kind of for simplicity, I'm going to put everything in terms of X, which in this beginning part is just going to be the horizontal direction. Okay, when we go to gravity, things falling due to gravity, we're just going to change that X to Y. Okay, and it's really not that big of a deal. Okay, now this is going to be divided by the change in time. So again, that's really a delta T, but how many times, if you are timing someone, let's say with the stopwatch, do you start on any other time than 0? Okay, you can do that. You could just say, you could start your stopwatch, and then when you got to 3, you could say, all right, go. Okay, but that's usually not the case. Okay, and it can be, but that's why we're just going to use T. We're trying to simplify this. Okay. Now, this is essentially always the case, okay? If you're going at a constant velocity or not a constant velocity, this is always going to be the case. Now, when you have a constant acceleration, okay, this is also going to be V final plus V initial divided by 2, okay? And here is that caveat. Okay, this is okay. So this part right here is true if you have a constant acceleration. Okay, if it is not a constant acceleration, okay, some variable acceleration, then you're going to be in the realm of essentially calculus only, okay? Now, this obviously is just sort of an algebraic point of view, which could be derived from calculus as well, as we'll see. And we might have some other calculus ones, and if you guys will remember or reflect back, it's really pretty easy from a calculus point of view too. All right, and so our definition of acceleration, so that those 3 arrows as in kind of an equal sign, like that's really equal, okay? And in your book, they're defining that as the definition. So if you see 3 arrows like a super equal sign, they're saying, hey, this is the definition. This is the definition of that. And that is going to be the change in velocity over the change in time, okay, as the limit as t approaches 0. Okay, that sort of thing you're used to from a calculus point of view. So from a practical point of view, non-calculus, constant acceleration, this is going to be v final minus v initial over t. Okay, so this is what we're going to be using. And we're going to call this equation 1, and we're going to call this equation 2. And I will summarize that, and we're going to basically have 4 equations that we're going to use predominantly for the first for chapter 2 and chapter 3 before we get into forces. Okay, and from these two equations, we're going to derive the third and the fourth. Okay, and you could derive more as we'll see. Okay, and in fact, I'm just going to say here, acceleration is equal to v final minus v initial over t. Okay, and that will make it a little more straightforward. Okay, so equation. Well, we can just do it from here. So if A is equal to B and B is equal to C, then A is equal to C. Do you guys recall what that's called? What's that? Transitive property, but there's also something kind of in logic called a syllogism, and it's essentially the same thing, but you tend to hear syllogisms with words like I can't come up with that, but you'll kind of see that. All right, so what we can say is x final minus x initial over time is equal to v final plus v initial over 2, and this is where we are going to start. This is where we're going to start when we develop the third equation, and I'm going to change this equation, okay, and I'm going to call this equation v final is equal to v initial plus at. Okay, so this right here is just a change in that format, right? Okay, but now what I'm going to do is I'm going to replace this with that. Okay, and now from this we're going to get x final minus x initial over t is equal to this v final, which is v initial plus a t minus vi all over 2. Okay, would you guys
be over t?
Sorry, over 2, right?
If you're
so this is v final plus thank you, v final plus the initial over 2. Okay, thank you. All right, and so now what I want to do is I want to get this all by itself. Okay, so I'll kind of switch pens here, and we're going to multiply both sides by t. Okay, obviously it's going to cancel out on this side, and we're going to get x final minus x initial is equal to, I'm going to distribute this through, and I'm going to get vit plus at squared plus vit all over 2, right?
2t, right?
What's that?
Oh, no, you're right.
Yeah. And this is all one thing, so it's all over 2. And we can even change colors again. And now we're going to have x final minus x initial is equal to, we've got a VIT and a VIT, which is 2 VIT, 2 VIT plus AT squared all over 2. Okay, but this time I'm going to break it up here. So I've got two fractions that are both under 2. And we can see here that this one cancels out, okay? And now we're going to end up with, when we put this together, we're going to end up with equation number 3. And that is going to be x final minus x initial. And that is going to be equal to VIT plus 1/2 AT squared. All right, makes sense? So you guys could even see that we might call this delta x.
Or delta
Okay.
D.
And again, if we start with where x, the initial position is 0, then we can kind of just say, hey, our distance or a change, or sorry, our displacement or a change in position is equal to that. So you might see it even simplified a little bit more, but that is kind of where we're at. All right, are you guys good with that? Okay. All right. So now, you guys, I'm going to erase this. I'm going to erase this. And we're going to derive our fourth formula. We're going to derive our fourth formula. And again, what we're going to do is we're going to start with this equation, except what we're going to rewrite this one. We're going to rewrite this one as V final minus V initial over A is equal to T, okay? Just rearranging this one so we have T all by itself. And now, wherever I see T, which is right there, I'm going to replace that. I'm going to replace T with this, okay? So, and you guys, just for purposes now to make it a little bit simpler, I'm going to call that delta x. So I'm going to have delta x over V final minus V initial. We could also call that delta V, but I'm going to, as you'll see, I am going to change, I'm going to leave it like this, and that's going to equal to V final plus V initial over 2. All right, are you guys good with that? Okay, one last thing here. This acceleration is in the denominator of the denominator. So it can just go to the numerator, right? So we can just say that, and now we're good. And now we are going to multiply both sides by V final minus V initial. So it's going to cancel out on the left, V final minus V initial, okay? And in fact, we're also going to multiply both sides by 2. And so it'll cancel out here. And now what we will have down here is we're going to say have 2a delta x, 2a delta x, and that's going to equal to V, make sure that I'm still in the frame here, V final plus V initial times V final minus V initial. And
That's the final squared minus the initial squared.
yeah, and so as very, very good. So we can see here that this is the difference, or the difference of perfect squares, right? A squared minus b squared can be broken down into a plus b times the quantity a plus b times the quantity of a minus b, right? So we're just going to put it back. And this right here is going to turn into v final squared minus v initial squared.
Wait, shouldn't it be delta v squared?
No, because we have this we have that separation. We can't do that. and that's going to be equal to 2a delta x. I'm going to move this. I'm going to add vi squared, add vi squared, okay? And I'm just going to flip this around for our final here. And that's going to be v final squared is equal to v initial squared plus 2a delta x. And this right here is our fourth equation. That is our fourth equation. Now, we could derive a fifth equation. We could derive a fifth equation, and notice that when we were here, we separated out a v final to develop equation 3. And in equation 4, we separated out and substituted in the t. What we could do is separate the vi and then substitute it and go kind of through that same situation, which you can do, but it's kind of what we want to do is kind of to narrow it down to a palette of fewer equations, so it's not so confusing, and then you will get used to manipulating those 4 equations to derive or solve a lot of these problems. Okay, are we good there? Yes, sir.
So did you avoid using delta v so you can multiply the two different?
Yeah, and like we said up here, we could have said delta v there, but I wanted to point out that it was a difference of perfect squares, so that you guys would recognize that. All right, so now what we're going to do is I'm just going to kind of summarize this and to kind of give you some tips on how to do some of the problems that you're about to face next week. Okay, and we're going to have equation 1, which is going to be average velocity is equal to x final minus x initial over t, which is also equal to v final plus v initial over 2, okay? And again, this part right here has to be constant acceleration. This part here has to be constant acceleration. All right, equation 2, which is going to be, and I'm gonna write it in this form: v final is equal to v initial plus at. Again, constant acceleration. Okay. Equation number 3 is going to be x final minus x initial is equal to vit plus 1/2 at squared. And then finally 4 is going to be v final squared is equal to v initial squared plus 2a times x final minus x initial. Okay, if you want to kind of further try to sort of simplify that, you could put in delta x there, you could put in delta x here, you could put delta x in there. Okay, if that makes more sense to you. All right, now, so the way that I'm putting these four equations up there, if you want to derive that 5th equation here, you could certainly do that. These are good because these are good to have kind of right in front of you when you are working on these kinematic problems. Now, these kinematic problems, as you may remember from the week 1, lecture 2, and if you haven't seen that, it's going to be a lot simpler than this. But if you have all those equations in front of you, it's going to make the problems a little more straightforward or a little more organized. Okay, so here is one of the key things to understand when you are puzzled by what to do when you are stuck on one of these problems. Okay. Now, you will notice here that there is no acceleration. And by the way, this equation and this equation also are only work for a constant acceleration. Okay. So this one has no acceleration. So if you're reading a problem, and you know it's accelerating, but they don't give you the actual number or don't ask about it, then this might be the equation. And a lot of times you're going to just say that those two things are equal. Okay. And so sometimes they're going to ask for the average velocity over those times, but a lot of times you're going to use that to solve one or the other. All right, so we can see here that in this case here, there is no delta x in the second equation. There is no v final in the third equation, and there is no time. There is no time in the fourth equation. Okay, so that is really what those equations are. Okay, so usually what's going to happen in these type of equations, okay, is they are somehow going to give you three variables. Okay, and if they give you three variables, then you can solve for the fourth. Okay, so really here we've got delta x. We've got 1, 2, 3, 4 different variables. Okay, now if they don't give you the starting or ending position, okay, then they're really going to ask you for delta x. Okay, so really there's only 4 equations in there. And if we separate it here, we got 1, 2, 3, 4, 1, 2, 3, and then the rest of them have four different variables. So in any equations, you need one. You need to know one less than the total number of variables. Okay, so if you can find 3, it will set you free. Okay, so what I would like to do real quick, just to give you an idea here, is we will just make up a problem and we'll kind of do it. Does that make sense? Okay, so I think we'll get rid of this. And if we have, okay, a car at rest accelerates uniformly from 0 meters per second to 15 meters per second in 8 seconds. Okay. What is the acceleration? Okay. Now we can see here that we have 4 variables. Well, actually, no, 3, because when it says at rest, that should mean obviously that the 0 velocity. So sometimes you will not see this, and you will see accelerates uniformly to 15 meters per second. Okay. So there's going to be many variables that are not explicitly stated there that you still are going to know. Okay, and that would be an example of one of them. Okay, so oftentimes it is good to list the variables that we know. Okay, so we've got v final, v initial, time and acceleration. We know that's 0, we know that's 15, and we know that this is 8, but we don't know the time. Okay, so now we're going to kind of go over here, and the other variable, okay, the other variable that is missing is delta x, okay, or the distance or the whatever. But we know that the question's not asking that, right? The question's not asking that. So which equation do we want? Okay, well, we probably don't want equation 3 because we don't know what the delta x is, and they're not asking us for the delta x. We probably don't want equation 4 because we don't know the delta x, and they don't give us the delta x. So 3 and 4 are out. And if we look at equation number 2, okay, we have the final, we have the initial, we have time, and the only one we don't know is this one. So we should start with equation 2. And now we can say v final equals v initial plus at. Now, at this point, you could do this. You can do this in kind of however you want. Now, I would suggest that you get into the habit of manipulating algebraically your equation before you plug in numbers. Okay, and if you do that, you're going to get v final minus v initial divided by t, and that will equal to a. Okay, now. Usually there's a kind of a point in your math career, okay, that when you see this, the first thing you want to do is plug in numbers and then change it around, okay, and that's fine. But it's when you start multiplying, dividing, subtracting, and adding numbers within an equation, it's really easy to make a mistake when you are rewriting those numbers, okay? So it's very often a good idea to manipulate the equation around so that you're only plugging in numbers one time, and then you're going to solve for that. And again, that can be kind of uncomfortable. A lot of times when you are doing a problem, and a problem that is more complex, your brain is still working. Your brain doesn't know how to do it from start to finish. So by doing part of the equation however you want, that's kind of that process of which you are solving for. So don't feel badly if you're doing it this way, because sometimes that's just part of the thinking process. It's like, well, now I know that the acceleration is this, and now I can move on to the next part. All right, so we can say 15 minus 0 divided by 8, is it? Would equal the acceleration 3.75. 3.875. Sorry.
Yeah. 8.
Sorry.
3.875.
But it's only 1.875.
Oh.
Sorry, 1.875.
Yeah, because it'd be 1
meters per second squared. Okay, the units for acceleration are meters per second squared. I'll talk about that in a second. And also, I'm not going to get too hung up on significant digits, okay? But if we do look at significant digits, it would actually be 2 meters per second, because if we look back here to 8 seconds, that's the one with 1 significant digit, and we should, because we divided by that, it should be actually rounded to 1 significant digit. Now, I'm kind of doing this on the board. If you look in a lot of the equations that are in your book, they're going to say like 15.0 and 8.00, something like that. So they're typically, you're going to see more. You're going to see more numbers, so that when you round it, it's going to feel a little more natural. Because for some reason, people have a hard time saying 8. I mean, like you have 1.875. People have a hard time saying it's 2. Okay, but this is really 2 meters per second squared. Okay, and that's just due to the uncertainty, because these really remember that could really be somewhere between 7 and 9 seconds, right? If that's somewhere between 7 and 9 seconds, then we can't quite be so sure, so specific that it's 8.75. All right, and that's really where it comes from. Okay, yes, sir.
If the answer is simple enough as 15/8, can't we just keep it in that form?
Great question, and the answer is no. Okay, great question. The answer is no. Math would say you're going to leave it at a fraction. Science is going to say you're going to put it in a decimal. Okay, and the reason why is in math you're just dealing with numbers. Okay, in science you're dealing with measurements, quantitative measurements, and a quantitative measurement is going to have a number and a unit. And if it's a vector measurement, it's going to have a number, a unit, and a direction. And you guys may or may not have gotten to the little thing on scalars and vectors.
We did a bit of it.
And yeah, and you got a little bit of that. So, so we always in science, we always want to put it in a decimal because then we can see the number and we know where the uncertainty lies. We know through significant digits where the uncertainty lies. But that's a great question. So in math, you're obviously going to have decimals, and in science, you're obviously going to see fractions. Most of the time, when you're going to see fractions in science, are going to be from the original equations, and they are specific. They are specific at that point. Okay. So we're just going to bleed. We're going to bleed one more thing off of this particular example, and that might be,
What's the delta x?
yeah, how far did it go? How far did it go? And I'm going to sneak that right here because I have memorized those equations. Okay. Personally, I think that it is a good idea that you memorize those equations. Okay. Now, growing up, and you guys will probably recognize this in me a lot, is I am very ADD. Okay, so I would lose everything. I would lose a notebook. I would lose jackets. It drove my mom crazy, right? So at a certain point in my education, I had to memorize things because I lost everything. I would lose notebooks or I would start a notebook and then, regardless, that's a character flaw that also developed into a character strength or whatever. So I'm better at memorizing things. Okay. Some people are not. Okay. So although I think it's a good idea that you memorize it, because for me, that's really helpful, but for you, it might not. Okay. Most of the time, whenever you're doing problems or whatever, you're going to have access to those equations. When you have a test, I'm going to give you those equations, right? You might have to change it around, but for the most part, you're going to be good. Okay, so now we're going to look at that next part. Let's say we had B. It's just like how far did it go? Okay, now we are presuming in this one-dimensional motion that it was only going in a straight line direction. So that really means delta x, okay? And if you want to put it in D, so if we go, we know, okay, if we go back to these equations, we know time, we actually now know acceleration, we know the initial velocity, we know time. So we could use equation 3, very straightforward, okay? We know v final, v initial acceleration, so we could use equation 4. Okay, we know v final, v initial, and time. We could use equation number 1. Okay, so at a certain point, there's more than one choice. Okay, and I'm just going to use equation number 4. I'm going to use equation number 4, which is v final squared is equal to v initial squared plus 2a. And I could put in D, 2AD, okay, which is just distance or displacement. Now remember, distance and displacement are different things. One's a scalar and one's a vector, but if we're going in the same direction, okay, then they are going to be the same. So for this first chapter 2, if it's going in the same direction, then we can interchange that. And that's oftentimes why I will use D, because then I can call it displacement or call it distance, okay, without having to make that distinction. Okay, so now we can change this around and say V final squared minus V initial squared divided by 2A is equal to our distance or our delta X. Now I've manipulated that around. So now we can say 15 squared minus 0 squared divided by 3.75. 1.875 times 2, is that 3.75?
3 point, it would be 15 eighths, which would be 30 eighths, which is 2 and 6
But-
eighths.
So 15 squared is 225 divided by 3.75. That's going to be about 7.5, probably.
225 divided by
3.75. Sorry, 70, not 7. 70, around 75.
0.075 times 2 is 0.075 times 2 is 0.15. So then 0.8 times 2 is 1.6. So you add 1.6 to the 1. That's 2.6, and then you add what you got earlier, which would be the 1.5 to it. You're just getting what you got, 3.75. At least that's how I do it in my head.
I'm calculating overall that it's equal to 60. Okay, and Ibrahim, I like the fact that you're doing that in your head, and I see a lot of people. I kind of make it a game for myself. I kind of make it a game to try to do the math in my head, and you can see there that I kind of screwed up a little bit of that. But so now we can say that it went 60 meters, because how many significant digits is that 60 meters? It's only one significant digit, right? Now, notice that I did not use 2. I used this 1.875. Okay, so I think it's probably, and there's some argument in there. I'm going to go back to the calculated value that I use, okay, the 1.875, and not use the 2, and do the calculation and then round, okay, and then round at the very end. And I've certainly read some people that would argue against that, but I think from a consensus point of view, most scientists are going to kind of round at the end and not the beginning. And for the most part, it's going to come out to be the same. And if not, if it's that critical, then you actually going to have to go back and get a better measurement. So instead of having 8, we would have like 8.0. Okay, and if we had 8.0, okay, then we could put in a decimal point there, and then that 60 with a decimal point becomes 2 significant digits. And if this was 8.00 and 15.0, okay, then it'd be 60.0. We add another decimal point, then obviously we would use all 4 of those, and then we would end up with that. And it's just getting more and more precise, But the accuracy would stay the same. You guys good there? Does that seem pretty straightforward? So these are the kind of equations that you're going to see a lot of next week. And the only thing that we're going to add there is we're going to add in gravity. So when we drop things or throw things up. And when we get into two-dimensional kinematics, okay, which is going to also be next week, is now if we throw things, okay, we're going to have kinematics in the y direction and in the x direction at the same time. and we'll combine those. And to me, that's a lot more interesting. It's a lot more interesting in this one-dimensional stuff. All right, you guys, I think that's good for the lecture, and we will still have time to answer other questions, but I'm going to stop the video.